Hello, everybody, and welcome to this discussion on protein purification, whereby I'll be discussing ion exchange chromatography. So let me begin by discussing some of the governing factors for protein-ion exchanger interactions. Protein-ion exchanger interactions are governed by the charge of the protein in relation to the ion exchanger. It's also governed by the dielectric constant of the medium, and it's also governed by the presence of competitive ions. All of those three factors are important governing factors that govern the protein-ion exchanger interactions. Now let me discuss the pH of the buffer and its relation to the isoelectric point of target proteins in relation to the charge of the protein and the ion exchanger. So the pH of the buffer controls the net charge of the target protein and also controls the charge of the weak ion exchangers. Strong ion exchangers, on the other hand, are not influenced by pH values applicable to proteins. So here you can see a figure. You can see the net charge on the y-axis and you can see the pH on the x-axis. Here in the middle, you can see the isoelectric point of a given protein. What we have to recognize is that when the pH is lower than the isoelectric point, that is, when the pH is lower than the isoelectric point of the protein has a net positive charge and it binds to a cation exchanger. On the other hand, when the pH of the buffer is greater than the isoelectric point of the protein, then the protein has a net negative charge and thus it binds to an anion exchanger. Keep in mind that a cation exchanger is one that has negative ion exchange resins, and an anion exchanger is one that has positive ion exchange resins. There is an important effect called the Dannon effect. The Dannon effect is when you have a significant difference between the pH of a buffer solution and the pH of the ion exchanger surroundings. So if a cation exchanger attracts positively charged protons and repels hydroxides to a sufficient degree, then that decreases the microenvironment pH relative to buffer solutions. And if an anion exchanger attracts hydroxides and repels protons to a sufficient degree, then that increases the microenvironment pH relative to a buffer solution. So let me discuss that in further detail. Let me draw a column here. Let's say we have an anionic ion exchange resin with a positive charge here. What happens here is the buffer has a certain pH, but the microenvironment pH surrounding the ion exchanger can be lower or it can be greater than the pH of the buffer solution. So an anion exchanger can increase the microenvironment pH relative to the buffer solution. And if you had a cation exchanger, then this could decrease the microenvironment pH relative to the buffer solution. Let me talk about alternate binding with relation to protein-ion exchanger interactions. So target proteins don't continuously bind to ion exchangers. Target proteins adsorb, then desorb, then adsorb, and so forth and so on. And thus, the location of target proteins alternate between the stationary phase and the mobile phase, and non-target proteins would ideally remain in the mobile phase. The important thing to recognize here is that the target protein doesn't continuously bind to the ion exchanger. It's going to adsorb, then desorb, then adsorb, and so forth and so on. And so this is a temporal relation. In a column, a particular target protein will bind to the ion exchange resin. Let's say this is a anionic ion exchange resin, and let's say you have the protein here with a net negative charge. It will bind briefly, then it will desorb, and then will adsorb again. And so this is the relation in terms of protein-ion exchanger interactions. This is the relationship that happens, and so you have what is called alternate binding. It's important to recognize the elution order of small molecules with relation to protein-ion exchanger interactions. So small molecules have a predictable elution time in accordance with the strength of the molecule-ion exchanger interaction. So as you increase the number of oppositely charged groups, you increase the adsorption time to the column. On the other hand, when we discuss proteins, the same phenomena is not adhered to due to the asymmetric charge distribution on the protein. So proteins with a net zero charge may bind to an ion exchanger. That's because if you imagine a protein and let's say we want it to bind to a column with a anionic exchanger, that is, it is positively charged, the protein could have a net zero charge, so it could be neutral. But what you have to recognize is that you can have negatively charged amino acids in this region of the protein, and this could potentially bind or interact with the ion exchanger. Similarly speaking, proteins with the same charge as the ion exchanger may still bind as well. So if we were to suppose that this protein is a net positive protein and it has negatively charged amino acids in this region, that can make the protein bind to the anionic exchanger that you see here. So you have to recognize that proteins are big. They are a little bit more complex when dealing with the predictability of their elution order. On the other hand, when you're dealing with small molecules, they have a predictable elution time in accordance with the strength of the molecule ion exchanger attraction. So here, for example, you have a series of small molecules and you have their elution order happening here. So here you have small molecules with various charges. This has a 3+ charge, this has a 2+ charge, this has a 1+ charge, this is neutral, and this is negatively charged. And here it is apparent that we have a cationic ion exchangers that you can see on the column. And so this small molecule with a net 3+ charge will bind for the longest time. So it will adsorb and it will desorb, but only after a long time relative to the other small molecules that you see here. Ideally, the negatively charged small molecule that you see here and the neutral charged small molecule that you see here will not bind to the cation exchangers that you see here. And so their elution order can be predicted because they're small molecules and they have a predictable elution time in accordance with the strength of the molecule ion exchanger attraction. That is, as you increase the number of opposite charge, you increase the adsorption time. So this small molecule would have the greatest adsorption time. This one would have the second greatest adsorption time. This would have the third greatest adsorption time. And these ideally would not adsorb to the cation exchanger. So here you can see this small molecule with a net 2+ charge having a greater adsorption time and thus a greater elution time than this small molecule with a net positive charge, and also it will have a greater adsorption time and thus a later elution time, or an elution order that is later in temporal scale than the negatively charged small molecule that you see here and the neutral charged molecule that you see here. Let me discuss the dielectric constant of media. So electrostatic interactions are proportional to the inverse of the dielectric constant. Typically, aqueous solutions are used for ion exchange chromatography, and sometimes organic solvents are used as additives. So the addition of organic solvents decreases the dielectric constant. When you decrease the dielectric constant, this increases electrostatic interactions and thus increases solubility of hydrophobic proteins. This is the reason that sometimes you add organic solvents when you are performing chromatography. And so examples of organic solvent additives that can be used include methanol and acetonitrile. Here you can see methanol, and you can also see the structure of acetonitrile for your reference. And lastly, I want to discuss competitive ions. I'll keep this brief and simple. As you decrease the concentration of competitive ions, and this will facilitate binding of the target protein to the column. When you increase the concentration of competitive ions, they will compete with the target protein, and this will facilitate displacement or desorption of the target protein from the column. I think this is simple and intuitive to understand. Now, what you have to recognize is that there are factors to consider during the elution of competitive ions. Typically, the concentration of these competitive ions is less than 1 molar. And what you have to recognize is that the concentration of those ions is an important factor to consider when eluting the proteins of interest. There's also the type of ion that you have to keep in mind. And counter-ion elution strategies can be summed up into 2 strategies. There is gradient elution and there is step elution. These are the 2 basic classes of elution that you can perform: gradient elution and step elution. And this concludes this module on ion exchange chromatography as an introduction.